Welcome to Journey Through Time, where we travel to the most mysterious corners of the cosmos and history. Today we begin an incredible journey beyond Earth, into places where chemistry and astronomy merge into one cosmic spectacle. Deep within our galaxy, near the supermassive black hole Sagittarius HE, lies a giant cloud of gas and dust known as Sagittarius B2. Hundreds of times more massive than the Sun, it contains a cocktail of astonishing organic molecules. Among them is ethyl formate, the same compound that gives raspberries their flavor and contributes to the aroma of rum. This isn't metaphorical but literal. In the vacuum between the stars float molecules identical to those we know on Earth. Astronomers detected them using powerful radio telescopes, reading the unique chemical fingerprints hidden in the spectrum of light. This discovery proves that complex organic chemistry arises naturally in space. Such molecules, the very building blocks of life, may be present throughout countless star systems. Sagittarius B2 is more than just a cloud. It is a cosmic kitchen where new stars and planetary systems are forming. Scientists have found amino acid precursors and carbon-based compounds relevant to biology, existing under extreme conditions without any biological processes at all. This changes how we think about the origins of life. If life's molecules are widespread, then life itself may be a universal phenomenon rather than an Earth-only fluke. Now picture another astonishing world, a planet so rich in carbon and under such immense pressure that its entire surface could be crystallized carbon, a literal diamond planet. Astronomers call it 55 Cancri E, a super-Earth located about 41 light-years away in the constellation Cancer. It's roughly twice the size of Earth and 8 times as massive, with conditions so extreme that carbon there may be compressed into diamond across vast regions. On Earth, diamonds form deep within the mantle under pressures millions of times greater than the atmosphere. Scale that up to an entire planet, and diamond formation no longer happens underground. It can happen everywhere. Models suggest that up to a third of this planet's mass could be diamond, trillions of carats more than all the diamonds ever mined on Earth combined. But this is no gemstone paradise. 55 Cancri E orbits its star at only 1.5 million miles, about 25 times closer than Mercury is to our Sun. A year there lasts just 18 hours. Temperatures on its star-facing side exceed 2,400 degrees Celsius, hot enough to melt iron, vaporize rock, and make mining impossible. Some evidence even hints at lava oceans, or an unstable surface venting carbon-rich gases into a thin, exotic atmosphere. The diamond planet challenges our assumptions about what a normal world looks like. It reminds us that the chemistry of other solar systems may be completely different from our own. Where Earth has silicates and water, other planets may have carbides, graphite, and diamond. Dozens of stars with similar carbon-rich compositions have been identified, suggesting diamond worlds could be common. These findings reveal the universe as far more chemically diverse than we imagined. Planets can be built from ice, metal, lava, or precious gems, showing that our home planet's combination of oxygen and silicates may be an exception rather than the rule. 55. Cancri E demonstrates how even distant starlight can reveal extraordinary worlds, and how a simple shift in chemistry can produce a planet that defies our imagination. Imagine hovering near the edge of a black hole, not falling in, just sitting nearby, and time itself slowing to an almost impossible crawl. To someone watching from a safe distance, you would appear frozen, while centuries or millennia ticked by elsewhere in the universe. This isn't science fiction, but relativity in action. Black holes bend not only space, but time, producing gravitational time dilation so intense that the closer you get to the event horizon, the slower your clock runs compared to someone far away. Einstein's general theory of relativity tells us that gravity curves space-time. Near a black hole, that curvature becomes extreme. From your perspective, your heart still beats and your watch ticks normally. But from a distant observer's view, your movements slow dramatically. In theory, by hovering close enough, you could time travel into the future simply by waiting, while everyone else races ahead. This effect has been measured even in small ways here on Earth. GPS satellites orbit slightly farther from Earth's gravity, and their clocks tick faster than those on the ground. A difference so real, engineers must correct for it, or GPS would stop working. Near a black hole, the effect magnifies enormously. The movie Interstellar depicted this idea accurately. A few hours near a supermassive black hole could equal decades elsewhere. From the outside, falling into a black hole is even stranger. As you approach the event horizon, you seem to slow down, redden, and fade, never quite crossing the boundary. But from your own perspective, you pass through without noticing anything special, heading inevitably toward the singularity, a point where physics as we know it breaks down. Inside, space and time switch roles. Moving forward in time becomes moving inward toward the center. Escape becomes as impossible as reversing time itself. Black holes are more than destructive traps. They are laboratories for the extremes of reality, revealing how flexible space-time truly is. They show us that time isn't a universal constant, but a malleable dimension woven into gravity, motion, and energy. A cosmic reminder that the rules of everyday life break down under sufficient mass and pressure. Take just 1 teaspoon of material from a neutron star, and it would weigh about 1 billion tons. The mass of Mount Everest squeezed into a sugar cube. Neutron stars are the remnants of massive stars that exploded as supernovae. When a star, 8 to 20 times the mass of our Sun, runs out of fuel, it can no longer resist its own gravity. Its core collapses, forcing protons and electrons to merge into neutrons, creating an object only about 10-20 kilometers across, yet more massive than the Sun. This is matter at its most extreme. No empty space between particles, only a dense quantum soup of neutrons, and perhaps even more exotic particles, like quark matter. The surface of a neutron star may be a crust of crystalline iron, only a few hundred meters thick, beneath which lies a superfluid of neutrons. Even a tiny piece would instantly sink through Earth's crust and vaporize everything nearby if teleported here. Yet these stars are also astonishingly dynamic. Some spin hundreds of times per second, producing beams of radiation so regular they rival atomic clocks. These pulsars sweep space like cosmic lighthouses. The magnetic fields are mind-bending, up to 1 trillion times stronger than Earth's, powerful enough to distort atoms and disrupt electronics at vast distances. In rare cases, magnetars push these effects even further, producing bursts of energy that can affect the chemistry of entire regions of space. Now travel even farther, to HD 189733b, a so-called hot Jupiter, about 64 light-years away. From a distance, its bright blue color looks inviting, but that hue comes from tiny silicate particles, the same material as glass, suspended high in its atmosphere. This planet rains molten glass, driven sideways by winds reaching 8,700 km/h, 7 times the speed of sound. Because it is tidally locked to its star, one hemisphere is in perpetual daylight at over 1,000 degrees Celsius, while the other sits in eternal night, creating temperature gradients that drive monstrous jet streams. Astronomers detected these conditions by studying how the planet's light changes as it passes in front of and behind its star, revealing its chemical composition and atmospheric motion. These discoveries push our understanding of weather, matter, and energy to the limit. Where Earth's storms are chaotic but survivable, HD 189733Bs are made of molten shards ripping across the sky. Where our mountains are massive, a neutron star's teaspoon outmasses entire continents. Such contrasts remind us that the cosmos is stranger than fiction, filled with extremes that seem impossible until measured. Even the age of the universe itself is tested by such findings. Some stars, like the Methuselah star HD 140283, have appeared older than the universe's calculated 13.8 billion years, forcing astronomers to refine their models and distances. New data has revised these ages downward, but the mystery remains close enough to challenge cosmology. Each anomaly, from ancient stars to exotic exoplanets, pushes scientists to re-examine the foundations of physics and how matter, time, and gravity interact. Together, neutron stars, diamond planets, glass rain worlds, and nearly timeless stars tell a consistent story. The universe is not built to our expectations. It produces objects and phenomena beyond the limits of common sense. And yet, through observation and analysis, we can measure, describe, and begin to understand them, one extreme discovery at a time. Look deep enough into the universe, and you discover something even stranger than neutron stars or glass rain worlds. Most of the cosmos is invisible. Everything we can see, stars, planets, gas clouds, galaxies, every atom ever observed, makes up only about 5% of the total mass energy content of the universe. The remaining 95% is dark matter and dark energy, two invisible forces that shape everything while eluding direct detection. Dark matter first revealed itself in the 1930s, when astronomers noticed galaxies spinning too fast. Their outer stars moved as though an unseen halo of mass was holding them together. Later, gravitational lensing, light bending around invisible structures, confirmed it. About 27% of the universe seems to be this mysterious dark matter, which neither emits nor absorbs light. It interacts mainly through gravity, and despite decades of searching for exotic particles, like WIMPs or axions, we still don't know what it is. Then there's dark energy, even more baffling. In the late 1990s, two independent teams discovered that the expansion of the universe wasn't slowing down. It was accelerating. Some unknown force, making up about 68% of the universe, is pushing galaxies apart, accelerating the very fabric of space. It might be an intrinsic property of space-time, a cosmic constant, or something entirely new. Whatever it is, it dictates the universe's long-term fate, possibly leading to a big rip, where galaxies, stars, and atoms themselves are torn apart. All of this means that our familiar reality is just a thin surface floating on an ocean of mystery. Satellites like Planck and Euclid map these invisible components indirectly, while particle colliders smash atoms to glimpse new particles. Each new measurement reminds us how little we know. The universe is 95% missing, yet its gravitational pull, its acceleration, and its large-scale structure are undeniable. And as the universe expands, galaxies dance on an even larger stage. The Milky Way itself is hurtling through space at about 600 kilometers, drawn by a mysterious gravitational anomaly known as the Great Attractor. Located 150–250 million light-years away, behind the dense center of our galaxy, this region pulls entire clusters of galaxies toward it. Infrared and X-ray observations reveal massive galaxy clusters like the Norma cluster, but much remains hidden behind dust and gas. Beyond even the Great Attractor lies the Shapley supercluster, an even larger concentration of mass. This cosmic tug-of-war shows that galaxies don't just drift apart. They move in great streams, shaped by structures we can't yet fully map. On human timescales, space seems still. But on cosmic timescales, collisions are inevitable. In about 4 billion years, the Milky Way will merge with the Andromeda Galaxy. Despite the drama of two massive spirals colliding, very few stars will actually hit each other because the distances between them are so immense. Instead, gravitational forces will warp and stretch both galaxies, flinging stars into new orbits and eventually merging their central black holes. The night sky from Earth, if Earth still exists, will transform into a breathtaking panorama of twisted stars and glowing streams, a slow-motion ballet of entire galaxies combining into one giant elliptical system. Even our definition of planets is challenged by discoveries of rogue planets, worlds with no stars at all. PSO J3 18.522, for example, drifts about 80 light-years away, without a parent star, 6 times the mass of Jupiter, wandering in darkness. Some may have been ejected from solar systems during early chaos. Others may have formed directly from interstellar gas. These rogue planets could outnumber stars in our galaxy, billions of dark worlds with no sunrise or orbit, yet possibly retaining enough internal heat or thick atmospheres to harbor subsurface oceans and even microbial life. Each of these revelations, dark matter, dark energy, galactic flows, collisions, rogue planets, expands our sense of what's possible. They show us a universe in motion, full of hidden mass and unseen forces, where even the basic categories of star and planet are more fluid than we ever imagined. Even the fabric of space-time itself can break our intuitions. According to Einstein, nothing can travel faster than light through space. Yet, in the first fraction of a second after the Big Bang, space itself expanded faster than light. This period, called cosmic inflation, stretched the infant universe from subatomic to astronomical scales almost instantly. It solved key puzzles like the horizon problem, explaining how opposite ends of the observable universe look nearly identical in temperature and structure, despite never having been in contact under normal light-speed conditions. Inflation also flattened the geometry of space, making the cosmos appear strikingly flat to our measurements today. Its fingerprints remain in the cosmic microwave background, the faint afterglow of the Big Bang, etched as tiny fluctuations in temperature and density. The sheer scale of the universe defies imagination. There are more stars than grains of sand on every beach of Earth combined. Even with conservative estimates of 100 billion galaxies, each containing hundreds of billions of stars, the total number reaches 10^22 to 10^24, tens of thousands of stars for every grain of sand. Most of these stars likely host planets, meaning trillions upon trillions of worlds, many perhaps Earth-sized, some habitable, some utterly alien. A single teaspoon of sand could symbolize tens of thousands of entire solar systems, each with its own storms, moons, and chemical cycles. This staggering scale shifts our sense of rarity. Life elsewhere becomes not just possible, but statistically compelling. Yet even familiar sights are less eternal than they appear. Saturn's rings, once thought to be as old as the solar system, may be younger than the dinosaurs, perhaps only 100–200 million years old. Composed mostly of pure water ice, they should have been darkened by cosmic dust over billions of years, but remain strikingly bright and clean. Cassini spacecraft measurements showed their mass is lower and their structure more fragile than expected, implying they are temporary, perhaps formed from a shattered moon or comet that wandered too close and was torn apart by Saturn's gravity. And they are disappearing. ring particles slowly spiral into Saturn as ring rain, meaning in another 100 million years, the planet may lose its iconic jewelry entirely. We are living in a cosmic moment, an astronomical blink, when Saturn just happens to be wearing rings. Scale also surprises us closer to home. The average Earth-Moon distance is about 384,400 kilometers, wide enough to line up all 7 other planets of our solar system, side by side, with room to spare. This mental image reveals how empty space really is. The Moon feels close, but the gap is enormous by human standards, a gulf so vast that it dwarfs entire planetary diameters. Temperature, too, can defy expectations. Venus, though farther from the Sun than Mercury, is the hottest planet in the solar system. Its atmosphere of 96.5% carbon dioxide, 90 times thicker than Earth's, creates a runaway greenhouse effect that traps heat at a nearly constant 464 degrees C across the entire planet. Mercury, with almost no atmosphere, experiences wild temperature swings, but averages cooler overall. Venus's hellish surface, pressure equal to 900 meters underwater on Earth, and clouds of sulfuric acid destroyed Soviet landers in under 2 hours. Yet it may once have had oceans billions of years ago, a reminder that planetary climates can change catastrophically and serve as warnings for our own. Even Earth's relationship with the Moon isn't as solitary as we think. Occasionally, our planet picks up a second moon, a tiny asteroid caught temporarily in our gravity, looping around for months or years before drifting away. In 2020, astronomers confirmed 2020 CD3, a car-sized object that had been orbiting Earth since 2017. These mini-moons are small, dim, and hard to detect, but may be common, offering potential stepping stones for future exploration or resource mining. At the center of it all, the largest stars dwarf our Sun beyond comprehension. Red supergiants like UY Scuti swell to radii 1,700 times larger than the Sun's. If placed in our solar system, such a star would engulf Jupiter's orbit and perhaps reach Saturn. Yet these giants are so diffuse that their outer layers resemble a tenuous mist rather than a solid surface. They are stars in their final throes, fusing heavier elements before collapsing, ultimately becoming supernovae or black holes. Their scale and instability make them some of the most dramatic actors in the cosmic story, reminding us that even stars are temporary, vast furnaces that burn, swell, and die, seeding the galaxy with the elements of future worlds. Taken together, these revelations show a universe in motion, ephemeral and extreme. Space is not empty, but alive with unseen forces and drifting worlds. Planets can rain glass, stars can weigh 1 billion tons per teaspoon, galaxies collide in slow-motion ballets, and even the laws of time and space can bend under gravity. And through it all, our telescopes, detectors, and imaginations are catching up, block by block, to a cosmos more immense and bizarre than anything we once dared to imagine. Across all these examples, from Sagittarius B2's chemical clouds to diamond planets, glass rain hot Jupiters, neutron stars, rogue worlds, and red supergiants, one truth emerges. The universe is endlessly creative, shaping environments and objects far beyond human experience. It shows us chemistry occurring naturally in the frozen darkness of space, planets made of crystal carbon, storms of molten shards at supersonic speeds, and stars so dense a teaspoon outweighs mountains. Each discovery pushes us further from our Earth-centric assumptions, forcing us to confront scales of time, mass, temperature, and distance that break ordinary comprehension. The gravitational tapestry weaving everything together stretches from the tiniest particle to the largest cosmic structures. Dark matter forms invisible scaffolding for galaxies, while dark energy accelerates their separation. Gravitational waves ripple outward from colliding black holes and merging neutron stars, carrying information about the most violent events in existence. Time dilation occurs not just near event horizons, but in everyday life, measured by atomic clocks on Earth and in orbit. Even our solar system is a transitory moment. Saturn's rings vanishing, Venus transformed from a potential twin world to a furnace, Earth acquiring and losing temporary moons, the Milky Way slowly falling into Andromeda's embrace. Space is also a story of hidden abundance. Rogue planets drifting unseen may harbor subsurface oceans. Mini-moons quietly circle Earth before slipping away. Thousands of exoplanets already discovered hint at billions more beyond our reach. Chemical building blocks of life appear in interstellar gas and comets long before planets form. The same processes that created Earth and its biosphere are playing out across the galaxy on unimaginable scales. Even familiar numbers become surreal. The distance to the Moon accommodates every other planet side by side. A year on 55 Cancri E lasts just 18 hours. UY Scuti's surface would engulf Jupiter. The Great Attractor pulls entire galaxy clusters without showing its face. And the early universe expanded faster than light itself. These facts are not science fiction metaphors, but carefully measured realities, derived from spectra, parallax, interferometry, gravitational lensing, and satellite data. In contemplating these extremes, we glimpse a universe where time and space are flexible, where categories blur, and where the seeds of life and matter are scattered like sparks across a vast and intricate web. Each phenomenon, whether a neutron star's billion-ton teaspoon, a gamma-ray burst's split-second brilliance, or a mini-moon's fleeting orbit, becomes a thread in a single cosmic tapestry, connecting atoms, planets, stars, and galaxies into one ongoing process. The more powerful our telescopes become, the stranger the universe appears. With the James Webb Space Telescope, the Extremely Large Telescope, and future missions, we will soon see exoplanet atmospheres in detail, trace the earliest galaxies, and perhaps even detect biosignatures light years away. This new era of observation promises to answer some of our oldest questions, while inevitably opening new ones, because each breakthrough also expands the horizon of mystery. We are living at a moment when our knowledge of the cosmos is exploding, when we can map invisible forces, detect planets without stars, and measure time itself, bending under gravity. The universe is not a static backdrop, but an evolving dynamic system, a vast laboratory of extremes. And as our understanding deepens, our place within it looks smaller, yet more connected, a reminder that the same forces shaping distant worlds also shape us here at home. Across the cosmos, everything is part of a continuum. The same hydrogen and helium forged in the Big Bang later fuse into heavier elements inside stars. Those elements are blasted into space by supernovae, forming new clouds, new stars, and new planets. Even the extreme phenomena we've explored, black holes, neutron stars, rogue planets, diamond worlds, are all chapters in this endless recycling of matter and energy. The universe doesn't just create once, it iterates, evolving structures on every scale, from quarks to galaxy clusters. One of the most astonishing aspects of this cycle is how the simplest building blocks can lead to the most complex outcomes. Ethyl formate drifting in Sagittarius B2 hints at prebiotic chemistry. Collisions between galaxies trigger bursts of star formation. Gravitational waves born from black hole mergers ripple across billions of light years. Each process is linked, each feeds into the next, weaving a cosmic network far larger than our ability to see. Our own solar system is a microcosm of this interconnectedness. The elements in your body were once inside massive stars that exploded long before the sun was born. Earth's oceans may have been seeded by comets rich in the same organic molecules found in interstellar clouds. The moon's craters record a history of bombardments that shaped our planet's evolution. Saturn's rings reveal how fragile and temporary celestial features can be, while Venus demonstrates how climate and atmosphere can utterly transform a planet. New technology is transforming our reach. Telescopes like James Webb and the upcoming Extremely Large Telescope are not only detecting exoplanets, but beginning to read their atmospheres, looking for signs of water, oxygen, and even potential biosignatures. Gravitational wave observatories are listening to the ripples of space-time from cataclysmic events. Networks of radio telescopes map the invisible scaffolding of dark matter through gravitational lensing. Each advance gives us a sharper, stranger portrait of reality. Ultimately, studying the universe is not only about what's out there, but about our own origins. Every exotic world, every bizarre star, every distant signal is a clue to how matter behaves under conditions we cannot replicate on Earth. These clues refine our theories of physics, guide our search for life, and remind us that our tiny blue planet is both ordinary and extraordinary, a participant in cosmic processes as old as time itself. As our understanding deepens, we begin to see patterns that transcend individual discoveries. The laws of physics, gravity, electromagnetism, quantum mechanics, are not just abstract rules, but the universal grammar shaping every star, planet, and particle. In Sagittarius B2, the same carbon-based chemistry that perfumes raspberries emerges in a frozen nebula. In neutron stars, the same nuclear forces that bind protons and neutrons on Earth compress matter to unimaginable densities. In hot Jupiters like HD 189733b, familiar silicate minerals become airborne shards of glass, driven by hurricane-force winds. These phenomena aren't isolated anomalies, but manifestations of the same principles, acting under extreme conditions. Consider time itself. Our daily lives assume a constant rhythm, yet general relativity shows that time flows differently, depending on gravity and motion. The difference is minuscule between a basement and a penthouse, but cosmic near a black hole, where minutes for you become centuries elsewhere. This flexibility turns time from an absolute into a local experience, reminding us that even something as fundamental as now depends on where you stand in the universe. Scale, too, is an enduring theme. A teaspoon of neutron star outweighs a mountain. The gap between Earth and the Moon can fit all the planets. Red supergiants like UY Scuti could swallow our solar system whole. Rogue planets may outnumber stars, and the Milky Way itself is only one among hundreds of billions of galaxies. These comparisons recalibrate our intuition, revealing how much empty space separates even the densest objects, and how much structure can arise from almost nothing. The search for life sharpens this perspective. If complex organic molecules arise naturally in interstellar space, and planets form in diverse, chemically rich environments, then life may be a byproduct of cosmic evolution rather than a rare accident. Subsurface oceans on icy moons, geothermal warmth on rogue planets, or atmospheres on exoplanets orbiting dim red dwarfs could all harbor some form of biology. Each discovery of water vapor, methane, or amino acid precursors adds another piece to this puzzle. Meanwhile, technology races ahead. Spectrographs dissect the faint light of exoplanets to reveal their gases. Gravitational wave detectors catch the invisible shudder of space-time from merging black holes. Space-based observatories map galaxies hidden behind the Milky Way's dust, and computer simulations model the birth of the first stars after the Big Bang. Together, these tools give us a time machine to the early universe and a microscope for the distant and unseen. Ultimately, the greatest revelation may be our own smallness, paired with our capacity to comprehend. From one planet orbiting an average star, using light that has traveled billions of years, we can infer the existence of diamond worlds, measure time dilation, and glimpse the invisible scaffolding of dark matter. Each new insight proves that while we are tiny in scale, we are immense in perspective, able to trace the universe's story from its first seconds to its far future. Across billions of years, the universe's extremes are not just curiosities, they're signposts showing how everything evolves. Black holes grow as galaxies merge, swallowing stars and gas, shaping the dynamics of entire clusters. Neutron stars spin down, releasing their rotational energy as powerful magnetic storms. Red supergiants shed their outer layers, enriching space with heavy elements that will seed future solar systems. Even dark energy, invisible and unfelt, sets the stage for the cosmic future, determining whether galaxies remain bound or drift forever apart. We've begun to see that the line between destruction and creation is blurred. A gamma-ray burst, the most violent explosion known, can obliterate life on nearby planets, yet also produce conditions that scatter elements essential for new worlds. Supernovae can sterilize regions of space, but also forge and disperse the iron in our blood. Collisions of neutron stars produce both deadly radiation and heavy metals like gold and platinum. Cataclysm and genesis are two sides of the same process. Technology allows us to watch these processes in real time. Telescopes capture the afterglow of distant supernova and track the light curves of exoplanets transiting their stars. Gravitational wave detectors sense ripples from collisions billions of light-years away, turning space-time into an observable medium. Radio arrays map neutral hydrogen across cosmic time, revealing the skeleton of the cosmic web. High-energy observatories register cosmic rays and neutrinos arriving from intergalactic space, giving us direct messengers of the most extreme events. As our data multiplies, the big picture comes into sharper focus. The Milky Way, with its spiral arms and star-forming regions, is one small thread in a vast tapestry of galactic filaments, superclusters, and voids stretching beyond our observable horizon. Our solar system, with its tidy orbits and familiar planets, is only one outcome of countless possibilities. Planets can form from radically different starting materials, producing diamond crusts, lava atmospheres, or glass storms instead of oceans and air. Life itself may find pathways we cannot yet imagine, thriving without sunlight, photosynthesis, or DNA as we know it. The ultimate implication is that the universe is not static, but experimental. It tries every configuration: stars of all sizes, planets of all chemistries, and systems of all dynamics. It folds time, warps space, and scatters matter in patterns both chaotic and precise. Our role as observers is to detect, decode, and connect these patterns, turning light from impossibly distant sources into stories about our shared origins. And through it all, one constant remains: curiosity. From ancient sky watchers charting the planets to modern astronomers mapping the cosmic microwave background, humanity has always sought to understand the heavens. Each new discovery is another step on that continuum, linking our ancestors' first questions to our descendants' future voyages beyond Earth. We are part of the same cosmic narrative we're trying to decipher. The more we learn, the clearer it becomes that every discovery is connected to a larger framework. The detection of organic molecules in deep space ties directly to the composition of comets and meteorites in our own solar system. The study of rogue planets hints at unseen reservoirs of mass drifting through interstellar space, which in turn affects our models of galaxy formation. Even the measurement of time dilation near Earth's surface informs our understanding of gravitational wells around black holes. All these separate observations converge into a single evolving map of reality. This convergence shows up in our understanding of cosmic cycles. Stars form from clouds of gas, enriched by previous generations, then burn and explode, scattering new elements. Planets condense from leftover dust and gas, sometimes holding on to atmospheres, sometimes losing them to space. Some planets are ejected, becoming rogues. Others maintain delicate orbits and stable climates long enough for life to emerge. Gravity shapes every stage of this process, collapsing gas into stars, corralling planets, stirring galactic flows, and even bending light to create natural telescopes through gravitational lensing. Another thread is scale and perspective. Consider the Great Attractor and the Shapley supercluster. These massive structures influence the motion of entire galaxy clusters. Yet from our vantage point, we see only hints of their presence behind veils of dust. It's as if we are reading shadows cast by invisible giants, inferring their form by the distortions they leave behind. Our instruments, infrared detectors, X-ray observatories, radio telescopes, peel back those veils, layer by layer, gradually revealing a three-dimensional web of filaments, nodes, and voids extending hundreds of millions of light-years. This three-dimensional web changes how we think about isolation. Even rogue planets adrift in the dark are not truly alone, but part of larger gravitational flows. Even the most distant galaxies feel the pull of unseen structures. And even here on Earth, our lives unfold within this gravitational and temporal fabric, subtly influenced by the same cosmic principles. We inhabit not a detached corner, but a dynamic, interconnected system that extends far beyond our sky. Such realizations have practical consequences. Understanding stellar evolution guides our search for habitable worlds. Mapping dark matter halos helps predict where galaxies form. Studying exoplanet atmospheres teaches us about greenhouse effects, climate feedbacks, and potential biosignatures. The science of the extreme becomes a mirror for our own planet, offering both warnings and possibilities. Finally, there's a philosophical resonance. Knowing that our planet's oceans may have been seeded by the same molecules drifting in interstellar space blurs the line between here and out there. It reframes life as a cosmic process rather than a local anomaly. The iron in your blood, the calcium in your bones, the oxygen in your breath, all forged in stars that died long before the sun was born. You are literally built from recycled stardust. This is not poetry, but physics, and it links your existence to events spanning billions of years and billions of light years. Every time we push the limits of observation, the universe answers with something stranger than expected. The first detection of an exoplanet showed a world nothing like Earth, a hot Jupiter skimming its star. The first gravitational wave event revealed two massive black holes spiraling into one another in the distant past. The first detailed image of a black hole's shadow confirmed Einstein's equations in the most extreme conditions. Each milestone shifts what we consider possible, expanding our mental map of reality. What makes these discoveries especially powerful is the way they connect disciplines. Astronomy, chemistry, physics, and biology converge when we analyze a distant planet's atmosphere for biosignatures. Engineering, mathematics, and computer science converge when we model galaxy formation or process terabytes of telescope data. Even philosophy and ethics enter the discussion when we consider the implications of finding life elsewhere or harnessing asteroid resources. This interdisciplinary web mirrors the cosmic web itself, a network of nodes and threads bound together by invisible forces. Looking at the sky through this lens, we realize that nothing exists in isolation. A rogue planet's lonely drift may have begun as a gravitational interaction between two giant worlds. A neutron star's incredible density is the end state of a massive star's life cycle. A galaxy's spiral arms form from waves of star formation, moving through gas clouds over eons. All of these processes have echoes and precedents in other corners of the universe, repeating with variations like cosmic themes. Even our own history as observers is part of the pattern. The ancient astronomers who tracked planetary motions laid the groundwork for Newton's mechanics, which in turn set the stage for Einstein's relativity, which then inspired the technologies we now use to test relativity itself. Our expanding knowledge is recursive. Each generation builds instruments to test the questions left by the previous one, and the universe responds with deeper mysteries. In this way, our exploration of space is also an exploration of time. Light from a distant galaxy shows us what it looked like billions of years ago. Gravitational waves arriving today carry information about mergers that happened before Earth existed. Studying Saturn's rings lets us witness a phenomenon just 100 million years old, still evolving. Every observation is a time machine, letting us see the past and predict possible futures. And yet, for all its immensity, the universe retains familiar echoes. Ethyl formate linking raspberries and rum to interstellar space. Diamond planets mirroring Earth's mantle processes on a global scale. Glass rain echoing volcanic shards in our own atmosphere. Gravitational time dilation turning science fiction into measurable fact. These correspondences remind us that the cosmos is not purely alien, but built from the same elements and governed by the same laws everywhere. Across the cosmic landscape, familiar principles create unfamiliar worlds. The same hydrogen that powers our sun blazes in blue giants, pulses in variable stars, and collapses into neutron matter. The same carbon that forms organic life on Earth crystallizes into entire diamond planets under alien pressures. The same silicates that make our beaches into sand become high-altitude glass shards, slashing sideways through exoplanet winds. These transformations are not isolated curiosities, but demonstrations of how matter, energy, and gravity interact at every possible scale. Take the merging of galaxies. To the naked eye, our night sky looks calm and still, but galaxies are constantly colliding, distorting each other's shapes, and flinging stars into long tidal streams. Our own Milky Way is on a direct path toward Andromeda, and over the next few billion years, the two spirals will stretch, twist, and merge into a giant elliptical galaxy. Yet despite the immensity of this event, most stars will never collide because interstellar space is vast. Instead, gravitational choreography will redistribute orbits, ignite bursts of star formation, and eventually settle into a new equilibrium. The central black holes will spiral together, releasing gravitational waves powerful enough to ripple spacetime across millions of light years. Zoom down to a smaller scale, and the same processes unfold. Planets migrate inward or outward as their host stars evolve. Some are ejected entirely, becoming rogue wanderers. Others lock tidally with their stars, turning one hemisphere into a perpetual day, the other into an endless night. Atmospheres evaporate under stellar radiation or become thick blankets of greenhouse gases. Magnetic fields shape the flow of charged particles, creating auroras or stripping atmospheres entirely. Each planet is a laboratory of chemistry and physics, sculpted by initial conditions and cosmic accidents. Even time itself participates in this layering of scales. Near a black hole's event horizon, time slows so dramatically that you could watch the universe race ahead while experiencing only minutes yourself. On Earth, atomic clocks measure nanoseconds of difference between mountaintops and valleys. In the early universe, space expanded faster than light, stitching causally disconnected regions into one smooth whole. This plasticity of time and space shows that what we take as fixed is actually malleable, responding to mass, energy, and motion. And behind everything, the invisible scaffolding of dark matter shapes the cosmic web. Galaxies form at its nodes, gas flows along its filaments, and dark energy pushes the fabric of space outward ever faster. These unseen forces hold more sway over the universe's structure and fate than all the luminous matter combined. Our observations, from gravitational lensing to cosmic microwave background mapping, are gradually sketching the outlines of this hidden architecture, but its true nature remains unknown. A reminder that our models are provisional, our understanding incomplete. Yet for all this strangeness, we can trace a single continuous story. Matter condenses, stars ignite, heavier elements form, planets coalesce, and complex molecules arise. Life may be one more stage in that process, emerging wherever conditions allow. And just as planets orbit stars, and stars orbit galactic centers, our own thoughts orbit these ideas, returning again and again to the question of how we fit into the vast pattern. This is why each discovery resonates beyond its immediate data. Saturn's youthful rings are not only a curiosity, but a clue to planetary dynamics. A rogue planet's lonely path hints at the violent rearrangements of early solar systems. A gamma-ray burst's blinding flash illuminates the physics of black hole formation. Red supergiants, swelling beyond Jupiter's orbit, foreshadow supernovae that will scatter new seeds of matter into space. Together, these observations form a mosaic of cosmic evolution, where every extreme event is also a creative act. All of these extremes, the invisible scaffolding of dark matter, the ripples of gravitational waves, the cosmic web of galaxies and voids, form a single evolving system. Matter, energy, and space-time themselves are in constant motion, cycling through stages of birth, transformation, and dissolution. Stars are born from gas clouds enriched by previous generations. They live, shine, and explode, forging heavier elements. Their remnants seed new clouds, new planets, and perhaps new life. Every element on Earth, every breath you take, every drop of water in your veins is part of this ongoing chain of stellar alchemy. Even the most exotic events carry echoes of familiar processes. A black hole devouring a star is a scaled-up version of accretion seen in young stellar systems. The spiral arms of galaxies mirror the density waves that shape rings in Saturn's icy debris. The magnetic storms on a neutron star resemble, in principle, the solar flares erupting from our own sun. These parallels suggest that the universe is not random chaos, but structured variety, with recurring themes at vastly different scales. Our instruments now reveal these connections in unprecedented detail. High-resolution spectrographs detect minute shifts in starlight, revealing exoplanets with Earth-like masses. Radio interferometers map neutral hydrogen across cosmic time, showing how the first galaxies assembled. Infrared telescopes pierce dusty regions to watch stars being born. Gravitational wave observatories capture space-time quakes from cataclysmic mergers billions of light-years away. Together, these observations transform the night sky from a scatter of lights into a living, evolving map. This map is also a history. Light takes time to travel, so distant objects are seen as they were long ago. A galaxy 10 billion light-years away shows us a snapshot from when the universe was young. The cosmic microwave background shows us the afterglow of the Big Bang itself. Observing the sky is like digging down through layers of cosmic archaeology, each photon a fossil carrying information from a different era. The farther we look, the earlier we see, until we approach the universe's first moments. At the same time, we discover how dynamic local space can be. Temporary moons orbit Earth unnoticed for years. Asteroids carry water and organics between worlds. Jupiter's gravity slingshots comets inward, seeding inner planets with volatiles. Even within our own solar system, processes echo the grand cycles of the cosmos, with migration, accretion, and resonance shaping planetary destinies. When we step back, a pattern emerges: universality. The same physics that governs an atom's electrons shapes a galaxy's spiral arms. The same gravitational dance that merges black holes drives the capture and release of mini-moons. The same chemical reactions forging amino acids in interstellar clouds occur in laboratories on Earth. We are not separate from the universe, but expressions of it. Condensed, conscious matter reflecting on its own origins. And because of that, each new discovery carries personal meaning. Seeing a black hole's silhouette or an exoplanet's atmosphere is not just an astronomical milestone, but a mirror, showing us how far our collective curiosity can reach. It underscores that, from one small world, with fragile instruments and fragile minds, we can detect forces operating across billions of light-years and billions of years. Every observation we make adds another piece to the grand narrative of cosmic evolution. By connecting these pieces, we're beginning to see the universe not as a collection of isolated objects, but as a single interconnected process. The galaxies flowing toward the Great Attractor are part of the same web that shaped the first stars. The organic molecules drifting in interstellar clouds today may one day seed oceans on planets not yet formed. The gravitational waves crossing our detectors are the echoes of collisions that forged heavy elements long before Earth existed. All of it fits into one continuous tapestry, stretching from the birth of time to its eventual destiny. In this tapestry, familiar boundaries dissolve. The distinction between here and there weakens when you realize the atoms in your hand were forged in ancient stars. The boundary between now and then blurs when you understand that looking into deep space is looking into deep time. Even the line between life and non-life becomes less clear when organic chemistry appears spontaneously across the galaxy, hinting at pathways to complexity wherever conditions allow. Each discovery also carries a lesson about humility. We once thought Earth was the center of everything. Then we learned the Sun is an average star on a spiral arm of an average galaxy. Now we see even our galaxy is just one of hundreds of billions, moving through a structure we can barely map, governed by forces we can't yet identify. This humility doesn't diminish us, it enlarges us, giving us a context in which our brief lives gain cosmic meaning. At the same time, our ability to understand and explore has never been greater. Instruments like the James Webb Space Telescope can detect the faint heat of distant exoplanets. Ground-based arrays can resolve radio signals from black holes at galactic centers. Particle accelerators can recreate conditions from the universe's first microseconds. Quantum experiments can test ideas about gravity and information at the smallest scales. Each of these technologies opens a new window, revealing layers of reality once hidden. These windows also let us see the future. We can predict the Milky Way-Andromeda merger. We can model how stars like the Sun will evolve into red giants and white dwarfs. We can estimate how dark energy might stretch space over trillions of years, leading to a cold, diffuse cosmos. Even if these predictions change with new data, they show that the universe is not an unknowable mystery, but a system governed by principles we can discover and refine. And through it all, patterns of beauty emerge. Spiral arms, ring systems, auroras, nebulae, planetary orbits, gravitational arcs, each is a visible expression of invisible laws. These patterns echo at every scale, from atomic lattices to galaxy filaments, suggesting a unity beneath the diversity. By tracing these patterns, we're not just cataloging curiosities, but uncovering the architecture of reality itself. Ultimately, studying the cosmos is a way of studying ourselves. The same curiosity that drives us to peer into the night sky also drives art, music, and philosophy. It reflects a uniquely human trait, the desire to know and to connect. Every measurement of a distant world, every spectrum of a faint star, every model of cosmic structure is a gesture of belonging, an assertion that even in the face of infinity, we dare to ask questions and follow where they lead. Standing back from all these details, we begin to see the universe as a living process, rather than a static stage. Galaxies grow like organisms, accreting material, merging and evolving over billions of years. Stars cycle through their lives, transmuting elements and scattering them back into space. Planets migrate, atmospheres transform, moons come and go, and chemical reactions proceed everywhere from deep interiors to frozen surfaces. Even the vacuum of space teems with quantum fluctuations, constantly creating and annihilating particles. Nothing is still. Everything is in motion. In this motion lies both destruction and renewal. When a supernova detonates, it can sterilize nearby systems, but also seed them with the raw ingredients for future worlds. When galaxies collide, they can tear apart stellar orbits, but also trigger waves of starbirth. When a black hole devours matter, it powers jets that can regulate galaxy growth. Every end state is a beginning in another form, an ongoing cosmic metabolism, converting energy into structure and back again. Seen this way, our own existence becomes a natural consequence of cosmic evolution. The carbon in our cells, the calcium in our bones, the iron in our blood, all came from stars that lived and died long before the sun. The water we drink may have been delivered by comets, formed in the cold outer reaches of the young solar system. The air we breathe is part of an atmosphere sculpted by billions of years of biological activity and geological feedback. Our planet is a node in a galactic network of matter exchange, and we ourselves are walking expressions of stellar processes. Technological progress now allows us to test these ideas directly. Missions sample comet dust and asteroid material, revealing amino acids and complex organics. Spacecraft map the interiors of giant planets, measure gravitational fields, and analyze magnetic environments. Ground and space observatories detect exoplanet climates, star formation histories, and gravitational waves from cosmic collisions. Together, these tools let us read the universe's autobiography, not just its headlines, but its fine print. And as we read, we find that the same laws apply everywhere. Whether on Earth or in distant systems, matter behaves according to the same constants. yet local conditions create dazzling diversity. This unity amid variation is the foundation of science. The idea that by studying one place carefully, we can infer truths about all places. It's also the foundation of wonder, because it means the night sky is not foreign territory, but a vast extension of our own story. Ultimately, each observation points to a bigger theme: interconnectedness. No molecule forms in isolation. No planet evolves without context. No galaxy moves without influence. The cosmos is a single unfolding whole, and we are part of its ongoing emergence, a brief but conscious expression of its capacity to self-organize and reflect upon itself. Each new advance in observation or theory enlarges the arena of our imagination. By mapping the cosmic microwave background, we glimpse the universe when it was less than 400,000 years old. By detecting gravitational waves, we hear the vibrations of colliding black holes billions of light years away. By analyzing starlight passing through exoplanet atmospheres, we infer their temperatures, compositions, and even the potential for life. These achievements show that, despite our small size and brief lifespans, we can reach across space and time to understand events unimaginably remote. This understanding is cumulative. The molecules found in distant nebulae link directly to the amino acids found in meteorites. The mechanics of star formation informs how planets coalesce from disks of dust. The dynamics of galaxy clusters reflects the influence of dark matter on cosmic scales. The same equations describe both the motion of moons and the orbits of entire galaxies. Science works because the universe is coherent, its laws applying everywhere, allowing us to test them here and apply them far away. This coherence does not erase mystery, it deepens it. We still do not know the true nature of dark matter or dark energy. We have not seen the first stars form or understood the ultimate fate of information inside black holes. We have only begun to explore the diversity of planets and the possibility of life elsewhere. Each discovery pushes our questions further out, enlarging the frontier. And yet, even as the frontier expands, the universe grows more personal. When we learn that the iron in our blood came from supernovae, or that Earth's water may be older than the sun, we realize that our individual lives are nested within cosmic history. We become participants in an unbroken chain of processes stretching back to the beginning of time. This perspective can change how we live, fostering a sense of connection to one another and to the planet that sustains us. The night sky becomes a record rather than a mystery. Every point of light is a story in progress, a star being born, living or dying, a galaxy colliding, a planet orbiting, a nebula dispersing. Our telescopes act as time machines, our equations as translations, our imaginations as bridges. This combination of observation, theory, and wonder allows us to reconstruct a universe that existed billions of years before us and will continue billions of years after. By studying the farthest reaches of space, we also discover the most intimate truths about ourselves. That we are made of the same matter as stars, that we live by the same laws as galaxies, that our consciousness arises from the same particles that build the cosmos. This realization is both humbling and empowering. Humbling because we are small, empowering because we can know. From the earliest human myths to the most advanced physics, our species has always sought to explain the sky. Ancient people tracked the wandering lights, built monuments aligned with solstices, and told stories about gods and heroes moving among the stars. Today we build particle colliders, space telescopes, and gravitational wave detectors, but the impulse is the same: to understand our place in a vast and mysterious cosmos. This continuity connects us across millennia, showing that curiosity itself is a force as persistent as gravity. In many ways, our search has only begun. We have mapped less than a fraction of the galaxy in detail, catalogued only a thin slice of the universe's planets, and glimpsed just the surface of cosmic phenomena. The deeper we look, the more variety we uncover. Planets with lava seas, stars with magnetic fields that shatter atomic structures, galaxies merging like living cells, filaments stretching hundreds of millions of light years. This diversity challenges us to abandon narrow definitions and embrace the unknown as a normal state of affairs. Yet despite all this, patterns recur. Rotation curves reveal hidden mass. Transits reveal hidden worlds. Spectra reveal hidden chemistry. By learning how to interpret light, gravity, and motion, we can reconstruct entire systems we will never visit. This power rests on the assumption of universal laws, and so far, the universe has rewarded our trust. Whether it is an exoplanet light years away or a particle collision in a laboratory, the same equations describe reality. One of the most profound implications of this universal consistency is the possibility that life may not be rare. If complex chemistry emerges spontaneously in cold interstellar clouds, and if planets form in profusion around stars of every kind, then biology may be a common cosmic outcome. It might take forms utterly unlike terrestrial organisms, using solvents other than water or chemistries beyond carbon. But the principle that matter organizes itself into complexity, given time and energy, could hold everywhere. Technology will soon test this hypothesis. Next-generation telescopes will analyze the atmospheres of Earth-sized exoplanets, searching for imbalances of gases that might indicate biology. Space missions will sample icy moons for subsurface oceans. Advanced observatories will detect faint radio signals from the early universe, tracing the moment when the first light pierced cosmic darkness. Each step moves us closer to answering the question that has haunted humanity since its beginnings. Are we alone? Even if the answer is yes, the search reshapes our understanding. It forces us to see Earth not as the center, but as one node in a galactic network, a fragile oasis sustained by cosmic processes. It sharpens our appreciation of our own biosphere and its precarious balance. It teaches us that the laws enabling life here also govern the rest of the universe, and that our own existence is neither an accident nor guaranteed, but part of a larger unfolding story. Seen through this widening lens, the universe becomes both more immense and more intimate. It is immense because of its scale. Billions of galaxies, trillions of stars, uncountable planets, cosmic structures stretching beyond our observable horizon. It is intimate because the same processes shaping those distant worlds also shaped us. The same star formation that forged heavy elements, the same chemistry that seeded life, the same gravity that holds everything together. We are not spectators, but participants in a cosmic drama, billions of years in the making. As we refine our instruments and our theories, we start to perceive not just the outlines, but the textures of cosmic history. We can trace the paths of galaxies, falling into superclusters, watch the flicker of light from stars being consumed by black holes, and detect the soft afterglow of the first atoms recombining in the newborn universe. Each measurement adds depth and detail to our portrait of reality, turning the sky from a two-dimensional dome into a dynamic, evolving 4D map of space-time. This deeper view also forces us to confront the limits of our knowledge. Even as we chart exoplanets by the thousands, we still know little about their interiors, climates, or potential inhabitants. Even as we model cosmic inflation, we remain unsure about its trigger or its end. Even as we detect gravitational waves, we are only beginning to understand what they can tell us about matter under the most extreme conditions. Each discovery reveals not only an answer, but a deeper question, an invitation to keep exploring. And yet, this endless questioning is itself a triumph. It means our methods work, our curiosity is fertile, and our civilization has reached a point where we can investigate phenomena across billions of light years and billions of years. From one small planet, using fragile instruments and finite lifespans, we are building a coherent picture of a universe vast beyond measure. In doing so, we are also rewriting our own story. We are moving from a narrative of isolation to one of connection, from seeing Earth as unique to seeing it as part of a grand continuum, from imagining the heavens as unchanging to understanding them as dynamic. This shift may be as profound as any scientific revolution, reshaping how we see ourselves, our responsibilities, and our future. Ultimately, these cosmic insights are not only about physics or astronomy, but about perspective. They remind us that while we are small, we are also rare in our ability to know. They invite us to humility and awe, to stewardship of our planet, and to solidarity with one another as fellow travelers through time and space. When we stretch our imagination to match the cosmos, we begin to see a seamless continuum from the smallest quantum fluctuations to the largest cosmic structures. The vacuum itself is not empty, but a restless sea of virtual particles flickering in and out of existence. These quantum tremors laid the seeds for galaxies during cosmic inflation, tiny irregularities amplified over billions of years into vast filaments and voids. The same physics that governs subatomic particles also sculpts the cosmic web, showing that reality is unified across an almost inconceivable range of scales. This unity reaches into our daily lives. The same nuclear fusion lighting the sun warms our planet and drives photosynthesis. The same gravitational pull that keeps the moon in orbit powers Earth's tides and subtly affects our clocks. The same quantum mechanics that defines the energy levels of electrons underpins the chemistry of life and the electronics in our devices. We are, in a literal sense, woven from the same principles that hold galaxies together and make stars shine. Even time itself, so basic to our perception, is revealed as elastic and local. General relativity shows that clocks tick differently in different gravitational fields or at different speeds. Quantum mechanics hints at connections between time, entropy, and information. Our familiar sequence of past, present, future may be an emergent property rather than a fundamental aspect of the universe. Each experiment testing these limits, from GPS satellites correcting for relativity to particle accelerators probing high energies, pulls back another layer of the curtain on reality's underlying fabric. When we apply this understanding to the search for life, a staggering picture emerges. The Milky Way alone may host tens of billions of Earth-sized planets in habitable zones. Many could have liquid water, stable climates, and atmospheres rich in complex chemistry. Some may orbit red dwarfs, others sun-like stars. Still others wander freely as rogue worlds warmed by internal heat. If the principles of physics and chemistry are universal, then the emergence of complexity, and possibly consciousness, may be a recurring phenomenon, a natural outcome of cosmic evolution. Technology is racing to meet these questions. Next-generation observatories will detect faint biosignatures in exoplanet atmospheres, measure the polarization of the cosmic microwave background, to probe inflation, and map dark matter through weak gravitational lensing. Space missions to icy moons will sample plumes from subsurface oceans. Ground-based detectors will catch high-energy neutrinos and cosmic rays from distant cataclysms. These projects extend our senses far beyond their biological limits, turning light, gravity, and particles into carriers of knowledge across space and time. Even as we gather this knowledge, the universe retains its power to astonish. Saturn's rings are younger than the dinosaurs. Venus once may have had oceans. Rogue planets drift by the billions. Neutron stars spin faster than kitchen blenders, yet pack more mass than the sun. Diamond planets glimmer under alien skies. Glass storms rage sideways at supersonic speeds. Black holes warp time itself, making the future of the universe flow differently, depending on your vantage point. These are not exaggerations, but measured realities, each one a data point in a growing cosmic atlas. Ultimately, the greatest revelation may be that everything is connected through cycles of energy and information. Stars form, shine, and explode. Elements disperse. Planets coalesce. Life emerges. Consciousness reflects. And eventually, matter returns to the stars. Even the most isolated phenomena, a gamma-ray burst, a rogue planet, a distant quasar, are embedded in this network, their behavior governed by universal laws. In studying them, we are also studying ourselves, because we are products of the same forces, animated by the same energy, built from the same matter. This recognition carries both humility and hope. Humility, because we are a single species on a small planet in a vast cosmos. Hope, because our minds can reach across billions of light years and billions of years, building a coherent story from faint signals and mathematical patterns. Each new discovery shows that our capacity to know is as extraordinary as the universe we are trying to understand. As our view of the universe grows, the distinction between local and cosmic fades. The same principles that guide planetary climates help us model exoplanet weather. The same plasma physics that explains auroras on Earth describes jets from black holes. The same gravitational dynamics that shape our solar system's minor bodies governs the migration of galaxies across superclusters. Knowledge at one scale informs the other, turning isolated facts into a unified narrative of how the cosmos behaves. This narrative also highlights impermanence. Every system, no matter how stable it appears, evolves. Stars burn through their fuel, planets shift orbits, atmospheres escape, galaxies collide, and even protons may eventually decay. What we see now is a snapshot of processes in motion, a single frame in a film, billions of years long. Understanding this impermanence changes how we see our own world, showing us that Earth, too, is transient. Its continents drifting, its climate shifting, its biosphere adapting or perishing, depending on conditions. At the same time, impermanence is the engine of diversity. Without stellar death, there would be no heavy elements. Without planetary migration, there would be no hot Jupiters or potentially habitable super-Earths. Without collisions, there would be no moons, no tilted axes, no stirring of atmospheres. Every catastrophe seeds new possibilities. Every destruction leaves behind materials for creation. This cycle is written into the fabric of the universe itself. Technological progress mirrors this cycle. Each generation of instruments supplants the last, producing clearer images, deeper surveys, and new ways of probing reality. Early astronomers used simple lenses to map the planets. Today, we use interferometers, spanning continents, and telescopes stationed a million miles from Earth. Soon, space-based gravitational wave detectors will open yet another window, listening to the low-frequency hum of the universe. With each upgrade, our picture of reality grows sharper and stranger. Our expanding knowledge also reframes the question of life. Instead of asking whether Earth is unique, we begin to ask how many pathways to complexity the universe allows. Could life arise in methane lakes, under ice crusts, or in high-pressure supercritical oceans? Could consciousness emerge from chemistries we have not yet imagined? Could civilizations thrive around red dwarfs, or as nomads on rogue planets? Each possibility widens the scope of our search and challenges our assumptions about habitability. And in this widening scope, a new kind of map emerges, one not only of stars and galaxies, but of processes and probabilities. We can estimate how often stars form, how frequently planets appear, how likely atmospheres persist, how long habitable conditions last. This statistical view treats life not as a rare miracle, but as an expected outcome under the right conditions, just another phase in the universe's ongoing experimentation. In embracing this view, we see ourselves differently. We are not a cosmic accident, but a cosmic expression, a temporary configuration of matter capable of self-awareness. Our curiosity, our instruments, and our theories are the universe looking back at itself, trying to understand its own origin and destiny. This perspective does not diminish the mystery, it deepens it, inviting us to continue exploring even when answers remain far away. Seen from the broadest perspective, the universe is a single unfolding experiment in complexity. Quantum fields fluctuate, producing particles. Particles bind into atoms. Atoms fuse in stars. Stars synthesize heavier elements. Elements form planets. Planets host chemistry. Chemistry crosses thresholds into biology. Biology evolves into minds capable of reflection. At each stage, new properties emerge that cannot be predicted from the parts alone. Superconductivity from electrons, life from chemistry, consciousness from neural networks. This hierarchy of emergence is as much a law of the universe as gravity or electromagnetism. This pattern of emergence appears at every scale. Spiral galaxies self-organize from rotating gas, echoing the way hurricanes form on Earth. Planetary systems arrange themselves into resonances and migrations, echoing patterns of orbital mechanics, repeated from moons to exoplanets. Stellar clusters disperse into the galactic disk like seeds carried by wind, echoing the spread of biological populations on a planetary surface. These analogies are not perfect, but suggest a unity of process, a fractal quality to cosmic structure and evolution. The implication is profound. The universe is not static, but generative. It does not simply exist. It produces. It tries configurations, discards some, stabilizes others, and builds upon what works, not consciously, but through the inevitable interplay of physical laws. This generativity means that what seems extraordinary to us may be commonplace on a cosmic scale. Diamond planets, rogue worlds, glass storms, time dilation, even life itself may be standard outcomes, not rare exceptions. Our technology is now reaching the point where we can test these ideas. High-contrast imaging can directly photograph exoplanets and measure their colors. Spectroscopy can reveal water vapor, methane, or carbon dioxide on worlds dozens of light-years away. Gravitational lensing can detect rogue planets in the dark between stars. Neutrino observatories can trace supernova cores as they collapse. Quantum experiments can probe the limits of space, time, and information. Each measurement is a glimpse into a process otherwise beyond our reach. As these measurements accumulate, they reshape our cosmology. We no longer see the universe as a sparse void dotted with islands of matter, but as a dynamic web of energy, matter, and information, constantly exchanging, recombining, and evolving. Galaxies flow like rivers. Dark matter filaments stretch like tendrils. Cosmic microwave photons carry whispers from the dawn of time. In this view, the universe becomes less an object and more a verb, an ongoing action, a perpetual unfolding. This unfolding places our own existence in context. Our planet's orbit, our species' evolution, our technologies, and our questions are all late blooms on a tree whose roots reach back to the Big Bang. The iron in our skyscrapers, the silicon in our chips, and the oxygen in our lungs are each products of stellar alchemy, billions of years in the making. Our capacity to know and wonder is itself a cosmic phenomenon, as natural as the orbit of a moon or the swirl of a galaxy. Recognizing this can be transformative. It suggests that learning about the universe is not a luxury, but a way of understanding ourselves at the deepest level. It suggests that our drive to explore and connect is not an anomaly, but an extension of cosmic evolution. And it suggests that while our individual lives are brief, our collective knowledge can become part of the universe's own memory. Patterns of information preserved across time, carried forward in technology, culture, and perhaps even future civilizations far beyond Earth. At the heart of this vast unfolding lies a paradox. The universe is both knowable and inexhaustible. Every time we uncover a principle, a new layer of mystery appears. Discovering exoplanets opens questions about atmospheres and climates. Detecting gravitational waves opens questions about neutron star interiors and black hole information. Mapping the cosmic microwave background opens questions about inflation and quantum gravity. This endless frontier means our curiosity will never run out of material. Each answer is a doorway to deeper exploration. This inexhaustibility also mirrors our own inner lives. Just as the cosmos contains layers of structure and history, so too do we carry layers of memory, culture, and imagination. Our myths about the stars, our physics of the stars, and our dreams of traveling to the stars are all expressions of one impulse: to connect. That impulse transcends eras and technologies, linking ancient skywatchers with modern scientists, poets with engineers, dreamers with builders. When we look up at the night sky, we are seeing photons that left their sources long before humanity existed. Yet by capturing and analyzing them, we extract information about distant worlds, ancient events, and fundamental forces. In this act, the universe becomes a text, and we become its readers. Telescopes, detectors, and equations are our tools of translation, turning faint signals into narratives spanning billions of years. This act of reading also transforms the reader. Knowing that the atoms in our bodies were forged in stars billions of years ago shifts our sense of identity. Knowing that planets and molecules form everywhere shifts our sense of uniqueness. Knowing that time and space themselves bend under gravity shifts our sense of permanence. These realizations can inspire awe, humility, and a renewed commitment to care for our own fragile world, which is both ordinary and irreplaceable. As our knowledge grows, so does our responsibility. The same science that reveals exoplanets also reveals climate change on Earth. The same orbital mechanics that predict rogue planets also predict asteroid impacts. The same technologies that probe dark matter can also be used to monitor our environment or explore other planets. Understanding the universe equips us not only with wonder, but with tools. Tools that can help sustain our civilization, protect our planet, and one day carry life beyond it. In this sense, cosmology is not escapism, but orientation. It tells us where we are in space and time, how we came to be, and what forces shape our future. It shows us that we are part of a cosmic continuum, inheritors of ancient processes, and participants in ongoing ones. It invites us to align our actions with long timescales and broad perspectives, cultivating stewardship rather than short-term thinking. Ultimately, each photon we capture, each spectrum we analyze, each model we run, is part of a dialogue between the universe and our curiosity. And as long as that dialogue continues, we remain connected. A small but luminous node in the great network of matter, energy, and consciousness. Thank you for traveling with us through the depths of space and time. From molecular clouds and diamond planets, to neutron stars, rogue worlds, cosmic webs, and the mysteries of dark matter and dark energy. Together, we've explored how the same forces that shape galaxies also shape our world and our very bodies, weaving everything into one vast cosmic story. Here on Journey Through Time, we believe that understanding the universe is more than a scientific endeavor. It's a way of discovering our own origins and future. Each new telescope, mission, and idea draws back the curtain a little further, revealing a reality that is both stranger and more beautiful than we ever imagined. As you reflect on the night sky, remember that every star is a story unfolding over billions of years, every planet a possible world, every photon a message from the past. We are all part of this cosmic narrative, atoms forged in ancient stars, minds capable of grasping infinity, travelers through space and time. If you enjoyed this journey, please like, subscribe, and share your thoughts below. Tell us where you're listening from and what time it is right now. We love hearing from our fellow explorers across the world. This has been Journey Through Time. Thank you for joining us. Until next time, keep looking up, keep wondering, and keep traveling through the universe with us.